Okay, hi everyone. So today we're going to be going through a practice exam for AAE 203. This is from spring 2022. Okay, so in the first problem we have a dimensional, oh my goodness. Okay, I have a dimensional analysis problem. So the first thing is to look at the information we're given. So we have all this information about some of the terms in this expression. And we want to find the dimension of, sigma? I think it's sigma, such that the following equation is dimensionally homogeneous. So I want to find the dimension of this term. So the first thing is we should take a look at our expression here that we have been given, and what does it mean to be dimensionally homogeneous? So this means that the dimension of the right-hand side of the equation equals, I should say left-hand side so it matches. The dimension of the left-hand side of the equation equals the dimension of the right-hand side of the equation. Okay, so looking at this, we have that we're given information about these variables. So it says r is a position vector. So that means that the dimension of r is going to be in length because it's measuring position. So this means length. Okay. The next one is that v is a velocity vector. So the dimension of v is going to be what is a typical unit, velocity is measured in meters per second, which is length per time. So this is time. Then we also have m is mass. So the dimension of m is going to be kilograms, for example. So that would be the dimension of m, which means mass. G is gravitational acceleration, so we have dimension of g. So what is g typically measured in? So if you ever get kind of confused about this, of what a term means, then think of like what a normal quantity would be. So we know it's kind of like 9.8 meters per second squared. So we know that it's in meters per second squared, which corresponds to length per time squared. X and y are lengths, so you measure length in, lengths, obviously. So we have the dimension of x is equal to L, and that's also going to be equal to the dimension of y because they're both lengths. And then finally we have t as time, so the dimension of t is just time, t. Okay, so now we need to find O sigma such that this equation is dimensionally homogeneous. So let's just kind of recall some of our rules, right? So first things first, if you have a division of two quantities, the dimension of that is going to be equal to the dimension of the top quantity divided by the dimension of the bottom quantity. The same thing applies for if you have multiplication, so you have g times t squared, so this is going to be equal to like the dimension of g times the dimension of t squared. So these are just some basic dimension rules that we apply, and this kind of should make sense, right? Because if you multiply like 9.8 meters per second squared by like 1 second squared, you should end up with 9.8 meters, which is in the form of which has a dimension of length. So let's start on the left hand side. So I'm going to delete this because we're going to go through this anyways. So on the left hand side, we want to find the dimension of r bar, the magnitude of r over gt squared sigma delta squared. Okay, so we can decompose this first. Let's look at this term. This term becomes dimension of r, the magnitude of this vector, divided by the dimension of gt squared. Then remember our multiplication rule that if we have two quantities a, b multiplied together, then the dimension of a, b is the dimension of a times the dimension of b. So this means we have dimension of this quantity here times the dimension of this quantity here times the dimension of this quantity here times dimension of delta squared. Okay, so then we can further decompose this into dimension let me write this here. The dimension of r divided by dimension g times dimension of t squared, which the dimension of t squared is just the dimension of t squared, times dimension of sigma times dimension of delta, and then we square this. So now we have an expression, and we know what these individual dimensions are, right? Because we found them from up here. So now we can say that, we can see that the dimension of the magnitude of r, knowing that r is a position vector, is going to be length. So we say this is L. The dimension of g, which we found here, is going to be length over time squared, times the dimension of t squared, which is just t squared, times dimension of sigma, which we don't know, times dimension of delta, which for now we don't know. So this simplifies down into, so the t squares cancel, and then the l's cancel. So we really just have on the left hand side, so the dimension of the left hand side for now is going to be equal to dimension of sigma times dimension of delta squared. Okay, so now let's tackle the right hand side, which is very ugly, but let me switch colors for that. So this is the right hand side. Oh, that looks pretty bad. Okay. Okay, so we have this double integral, and so remember that for integrals, oh wait, this is too light of a color. Okay, so for integrals, if you have something like y dx from like 0 to 5 or whatever, that's kind of equivalent of saying the area under this curve, right? Where let's say y is a function of x. So maybe from like, okay, that's not 0, so let's say 1 to 5. So from here to here, the integral is equal to the area under this curve, right? So that means that the dimension of an integral y of x dx is going to be equal to the dimension of y times the dimension of x, because this is just an area, right? So if you were to find this area normally, you would do something like x times y, for example. So that's how we know what the dimension of an integral is. So we can actually reduce these integrals into the dimensions. Okay, so we have dimension 0, 5, 0 delta, t squared, v squared, m squared, g squared, dx, dy. Okay, so knowing that these are integrals, this is kind of like our internal function, right? That's kind of like our y of x. So well, I shouldn't say y of x because that's probably a bit confusing with this variable here, but this is like our function f of x. So the first thing is we want to get rid of these integrals. So we know that the dimension of an integral is just equal to the dimension of this function here times the dimension of this quantity here. So we can reduce this to the dimension of, let's do this. So we can reduce this to the dimension of t squared, v squared, m squared, g squared times the dimension of x times the dimension of y. Right, so this is because we have a double integral, so you would just perform this process twice. And so after your first integral, you would have the dimension of this quantity times the dimension of x, which is the integral corresponding to this. And then for the second one, you would have the dimension of the internal quantity, which is now going to be this quantity, times the dimension of y. So that's why we have the dimension of x times dimension of y. Okay, so we've kind of reduced this down, and so the question though is this delta term. We want to figure out what that dimension is. So when you integrate, if you're going to integrate over, let's say, time, you're going to integrate from like 0 seconds to 10 seconds or something, right? So the dimension of these bounds is going to be the same as the dimension of the thing, of this delta of dt. So that means that the dimension of delta, so the dimension of delta, has to equal the dimension of the variable that you're integrating over. In this case, you're integrating over x for this first integral. So that means the dimension of delta equals the dimension of x. And we know the dimension of x is length from up here. Okay, so, whoa, that's very strange. Okay, so we know this information as well from this expression. So I'll probably write this as an aside. How do I draw this? I'm going to do this as an aside. Okay, so now on our right hand side we have the dimension of this entire quantity equals the dimension of this times the dimension of x times the dimension of y. So let's apply again our rules. So we know that dimension of any multiplication is just equal to dimension of each quantity multiplied by each other. So for example here that would be this times the dimension of g squared times the dimension of x times dimension of y. And we also know that when we have, a dimension of t squared, that's like second squared, right? So the dimension of t squared is equal to the dimension of t squared. Same thing for v and m. And then times dimension of x times dimension of y. Okay, so from above we know all of these quantities. So we have dimension of t is t. Dimension of v, which was the magnitude of the velocity vector, is just going to be not meters per second, length over time squared. I always get confused here because sometimes I think m as in like meters, so just maybe be careful of that if you're prone to forgetting that too. Dimension of m, so m is a mass, so that means it has dimension m squared, or it has a dimension of m, and then we square it to get the dimension of m squared. Then we know g is gravitational acceleration, which is measured in length per time squared. Square that. Dimension of x equals dimension of y, which is length times length. So this gives us, after we simplify, we have L squared times M squared times L squared over T to the fourth, which is just M squared L squared over T squared. Wait, no. M squared L4 divided by T4. Is that right? Yeah, okay, that's right. Okay, so just to recap, we found that the dimension of the left-hand side equals the dimension of sigma times the dimension of delta squared. Although now we know that delta from here is going to be L, so we can plug that in here to get that the dimension sigma times L squared equals whatever's on the right hand side, which is M squared L4 T4, which is from here. So now we can solve for dimension of sigma, which is equal to M squared L squared over T to the fourth. So this is our final answer for the dimension of sigma, such that this equation is dimensionally homogeneous. So I forgot to write this, but just as a final overview, what we did is we first find the dimensions of everything we've been given. So we know that, these are position, velocity, mass, acceleration, etc., which you can then write as, length over time squared, or in forms of the MLT. And then to find if the equation is dimensionally homogeneous, we know that this has to be satisfied. So we find the dimension on the right-hand side, we find the dimension on the right-hand side, apply our rules that we know about dimensional analysis, and we're able to set equal this final expression, which helps us solve for the dimension of sigma. Okay, so problem 2. Consider the following vectors expressed in the E-frame. So let's say we have our E-frame here. This isn't really necessary, but it just helps to visualize. So U is U1 E1 hat plus U2 E2 hat plus U3 E3 hat. Same thing goes for V and W. W is given as the cross product between U and V, and the angle between U and V is noted as theta. And then find an expression for tangent theta in terms of the components of the U, W vectors. Usually you know about dot and cross products. Okay. So let's see. So we know that it's the angle between U and V. Let's just visualize this. So let's say this is U, this is V, is equal to theta. Find tan theta. So when you see tan theta, what you might want to think about is that tan theta is equal to sine theta over cosine theta. And when I see sine and cosine theta, I think about like the magnitude expression for cross products and dot products. So those correspond to, for example, U dot V is equal to the magnitude of U times the magnitude of V cosine theta. And a similar thing happens for U cross V. So if we have U cross V, that's equal, so the magnitude of this is going to be equal to the magnitude of U times the magnitude of V times sine theta. These are two expressions that we know about dot products and cross products. So this theta also is going to be the angle between the U and V vector. Okay, so that's something we know about dot and cross products. So we can find tan theta by doing sine theta over cosine theta. So this can be written as cosine theta equals U dot V divided by the magnitude of U times the magnitude of V. And then sine theta can be written as U cross V magnitude of it divided by U magnitude times V magnitude. And just as a note, these bars represent the magnitude of something. So the magnitude of a vector is kind of like the length of a vector. Or not kind of, it is the length of a vector. Okay, I guess in 3D it would be like, or 2D, it would be, or even 1D, it'd be like the length of a vector. But maybe once you get to 4D, that's not the case anymore. But the point is, for the purpose of this problem, it is the length of a vector. And so now we can write tangent theta as sine theta over cosine theta, which is equal to U dot V over magnitude of U, magnitude of V, divided by, oh wait, I messed that order up. Hold on. So sine theta is equal to U cross V divided by the magnitude of U times the magnitude of V. Then we know cosine theta is U dot V divided by the magnitude of U times the magnitude of V. So notice that we can actually cancel out these two terms, right? Because it's just how it will work if you flip the fraction over to the top, and then you can cancel those two. So we end up with U cross V divided by the magnitude of U cross V times the dot, or divided by the dot product of U and V. Okay, that's a much nicer expression than what will happen next. But so first we know that U cross V is equal to W, right? We're given that here. So this is the magnitude of W divided by U dot V. What is the magnitude of W? The magnitude of W is equal to you sum up all the components in quadrature. So basically you square all the components and you add them together. And then you take the square root of all of that. That's the magnitude of W. So that's W1 squared plus W2 squared plus W3 squared. Okay, the next thing we need to find is this U dot V. So dot product, how does that work again? So u dot v is equal to, so we take, oh, okay, let's just calm down here. Okay, so we take okay, I'll just write this out actually. So we have u1 e1 hat plus u2 e2 hat plus u3 e3 hat dotted with v1 e1 hat plus v2 e2 hat plus v3 e3 hat. Okay, so when you take a dot product, what you do is you take the dot product of each term. So for example, you would have u1 e1 hat dotted with v1 e1 hat plus u1 v2 e2 hat, or wait, sorry, u1 e1 hat dotted with v2 e2 hat plus u1 e1 hat dotted with v3 e3 hat. So you would basically continue this, like distributing all of this forever. I'm just kidding. Until like you reach the end, obviously, when you have u3 e3 hat dotted with v3 e3 hat. But there's the fast way to know how to do a dot product is that you know that e1 dot e2 is going to be equal to 0, and e1 dot e3 is equal to 0, and e2 dot e3 is equal to 0, because they're going to be orthogonal. So we have, our e1, e2, e3 as this. So when we take the dot product between this vector and this vector, we get 0. So that's why the fast way to do the dot product is simply to do u1 v1 e1 hat dot e1 hat plus u2 v2 e2 hat dot e2 hat plus u3 e3 hat dot e3 hat. I'm missing a v3, so I'll just add it here. So this is, when you take the dot product, the only terms that aren't 0 are the terms where the vector direction, like e1, is the same as the other one. So you have e1 e1 e2 e2 e3 e3. So that makes our dot product a lot faster, so we can, like, once you know how the dot product works, you can just very comfortably write out that the dot product between u and v is equal to u1 v1 plus u2 v2 plus u3 v3. So that is what is equal to this. So then we end up with u1 v1 plus u2 v2 plus u3 v3. And this is our expression for tangent of theta. Okay. Ooh, let's see. Yeah, so just to again recap what we did. So first thing, we looked at these vectors, and it was slightly scary because they're a bit complicated looking. And we know that we need to find the tangent of theta. From tangent of theta, we know that's equal to sine theta over cosine theta. We're able to apply our rules about dot products and cross products, and then simplify that, plug these into tan theta, simplify, and then get into this form where you have, the vectors of u, v, and w in the expression. Then we simplify it into our components using what we know about magnitude and dot products, and then we end up with this expression. So yeah, that's this second problem. Okay, problem 3. So in the figure below, the ball B is rolling down the ramp at constant speed v. Reference frame E is fixed in the ground. The ramp rotates about a line fixed in E at constant angular velocity sigma. Okay, so let's write what we know so far. So we know that v is constant. What does that mean? That means that dv dt, which I will write in short as v dot, is equal to 0. The other thing we know is that the angular velocity is constant. So that means theta dot equals 0. We also know the angle theta and length L are fixed as well, so we have theta dot equals 0 and then L dot equals 0. Introduce a single reference frame and use the BKE to find the velocity of P and E and the acceleration of P with respect to E. Oh, I think that's a typo. Yeah, so this should actually be B, and this should also be B. So we want to find V of B and E and A of B and E. Okay. Jeez. Okay. Oh my goodness. Okay. So whenever you are approached why is it having, okay. So whenever you have this kind of problem, the first thing when we use a BKE is you want to establish a distance or position vector from a fixed point. So a fixed point with respect to the fixed reference frame to the point of interest. So in this case, you can choose your reference point to be like here, because technically it's not moving with respect to the reference frame E. But that's kind of hard and slightly confusing, because then you have to define the distance to the point of interest, which is B, to be like this whole thing. And that's kind of a complicated path, so we don't want to do that. So you want to choose the simplest location possible. So what's not really moving with respect to E? This point right here. Alright, it's at the center of the disk. It's not moving with respect to the E. It's just kind of like sitting there even as it rotates around. Even as like the disk itself rotates around. So I'm going to call this point O. And then I'm going to call point B, obviously B. So the first thing is to introduce our reference frame. So what kind of reference frame do we want to introduce? So I think in this case, the easiest reference frame to introduce would be in this, what do you call it? Disk? Okay, I'm just going to call it disk. So I'm just going to say that I'm going to introduce a frame here in the disk, which is, I'm going to call my A frame. So introduce A frame. Okay, well that sounds like introduce a frame, so maybe I'll just call it the B frame. Fixed in rotating disk. Okay, so I'm going to say this is my B1 hat vector, this is my B2 hat vector, and then by right hand rule, so imagine like so point your fingers in the direction of B1, then curl towards B2 using your right hand. And then your thumb should point in the direction of B3, which should be towards you if you're doing this correctly. So it should be out of the page and towards you. So this is like the general convention that we should follow because it just keeps things consistent. So we can do like an example with E. So let's say that this is my E1 hat, this is my E2 hat vector, and then this is going to be my E3 hat vector, right? Because if you point your hands in the direction of E1, rotate towards E2, your thumb should be pointing out towards you, which is in the direction of E3. Okay, anyways, so we've introduced a B-frame row fixed in the disk, and we've also introduced point O as fixed point with, let's say the fixed point in fixed reference frame E. Okay, also, why do we care about its fixed in E? It's because we're trying to find the velocity with respect to E, the velocity or the acceleration with respect to E. So because of that, we have to have a point that is fixed in E if we want to find the velocity with respect to the fixed frame. Okay, so now we have a frame that we've introduced, so we can write our position vector as O to B, which is equal to, so how do we get from O to B? You can first travel along here, and then you can travel up to B. So that means you go negative L along the B1 hat direction, and then you go up X. Okay, so this is a tricky part. So what is this vector right here? So you're going up by X sine theta, right? So this is our triangle. This is theta. This is X. X sine theta is here. X cosine theta is here. So we have X sine theta in the B2 hat direction plus X cosine theta in the B1 hat direction, right? Because we're going up in this direction, so we're traveling first this way and then we go up. So this is in the B1 hat direction and this is in the B2 hat direction. Okay, so now the way to get the velocity, right, you would take the derivative derivative of the position vector with respect to the fixed frame. Okay. Oh my goodness. How do I stop this from showing up? Okay, I don't know. Oh. Okay. What? Okay, I think okay, I think it's fine now. So now we have the velocity. So we said that as a derivative of the position with respect to the fixed frame. So how do you do BKE? So the BKE states that this derivative is going to be equal to the derivative of the position vector, or the vector that you're of interest, in the frame that it is currently written in. So currently we have written ROB in the B frame. So we write it as the derivative of the position vector with respect to B, the B frame. And then we add the angular velocity of the B frame with respect to the E frame. This is all with respect to frames, not with respect to the point. So that's why our angular velocity is in terms of the B frame with respect to the E frame. So that's why we don't put like a capital B here. That's incorrect, because the angular velocity is the angular velocity of the frame. Then we take that and then we cross product with it with the original vector, so ROB. That's the BKE. And just as a side note, the reason I write this in the B frame here, this position vector, is because this is spinning, right? So I cannot write it in terms of the E frame because this entire thing is spinning. So this L is not always pointing in the same direction as, the E1 hat. Even though in this instance it looks like it's pointing in the same direction as E1 hat, this distance right here is going to change as this disk rotates. So that's why you have to write it and introduce a B frame that rotates with the disk. So now let's do the BKE. So first we take the derivative with respect to the B frame of ROB. So that gives us negative L dot B1 hat plus X dot. Okay, so we have to product rule this. So we have, let me write this out. The derivative of X sine theta B2 hat plus the derivative with respect to the B frame of X cosine theta B1 hat plus, okay, what is omega B of E? So what is the angular velocity of B with respect to the E frame? So notice that this is rotating like this, right? So it's kind of hard to, well, you can't see me, so you also can't see which way my hand's going, but it's going around like this, right? So if you imagine curling your fingers, so curl your second, third, fourth, fifth fingers, right, of your right hand in that direction, you should find that your thumb is pointing upwards. So upwards as in it's going in the B2 hat direction. So here's the thing. I know people get confused about the arrows because it is confusing sometimes. In this case, because you see it's kind of like wrapping around this center thing, that means it's like your finger should be going like into the page, curling in. So that's why your thumb should be pointing in the B2 hat direction. So that means the angular velocity is in the direction that your thumb is pointing. So in this case, your thumb is pointing in the B2 hat direction. So you should have sigma, wait, is this, I don't, omega, yeah, okay, omega B2 hat as your angular velocity. And then we cross that with the original vector, which is here, so that's, I'm going to combine terms, negative L plus X cosine theta B1 hat plus X sine theta B2 hat. No, I can't. Let's do this. Plus X sine theta B2 hat. Okay. Oh, okay, that's a lot. So first, we know that L dot is equal to 0, right? So this term can drop. Now let's take the derivative. So we know that product rule, right? So we have X dot sine theta plus X cosine theta times, we have to also chain rule because theta dot could be changing. You never know. So this is our expression for B2 hat plus same thing for B1 hat, X dot cosine theta plus X times negative sine theta times theta dot b1 hat plus the omega b2 hat cross negative L plus x cosine theta b1 hat plus x sine theta b2 hat. I'm just copying this second term. So we know that theta dot is equal to 0. It's given in the problem statement. So this becomes 0. This also becomes 0 because theta dot is 0. So we're left with x dot sine theta b2 hat plus x dot cosine theta b1 hat plus this cross product term. So let's figure out this cross product over here. So I know there's a way that you can do cross, so it's like 1, 2, 3, back to 1. I think it's like it's positive, negative. Okay, wait, I don't remember. So the thing is, I never do cross products using this method. I just take the determinant because I think it's also the easiest. It's the most methodical and it's harder to mess up, I think. So what is a determinant if you don't know? So we just how to explain it? So we basically put the first vector, which is this, in the determinant form, which is you put the vectors on the first row, and on the second row you have the first vectors. So the first vector is equal to omega b2 hat, right? So you have 0, omega, 0. And then you have the second vector on the next row, which is going to be x, let's make some room, x cosine theta minus L, and then x sine theta, and then 0, right? Because it has x cosine theta minus L as the b1 hat component, and x sine theta as the b2 hat component. Okay, now we take the determinant. So how does that happen? So we first take b1 hat, then we multiply it by the determinant of, so we multiply it by the determinant of omega 0, x sine theta 0. So this is because you delete the column and row that you're taking the first term in. So in this case, our first term is b1 hat, so we delete that row and column, and we're left with the following matrix or terms, and so that gives us this determinant here. We do the same thing, but for b2 it's special because you have minus b2 hat times, I'll just write it on a new line. So for whenever you do b2 hat, you have to put a minus sign in front. It's just the rule. So we again delete the row and column it's in, and then you have 0, 0, 0, x cosine theta minus L. And then finally you have plus b3 hat times, let's delete the column and row again. So you delete the column that b3 is in and the row that b3 is in, and you're left with 0 omega x cosine theta minus L times x, not times, and then x sine theta minus L. And then let's simplify this. So the way you simplify a determinant is if you have, say, a, b, c, d, the determinant of that is going to be a, d minus b, c. So we apply that here, so we have b1 equals, so ad in this case is sigma times 0 minus 0 times x sine theta minus b2 hat, which is 0 times 0 minus 0 times all that jazz, which is equal to 0. And then we have plus b3 hat, which is 0 times x sine theta minus x cosine theta minus L times sigma, omega. Yeah, omega, okay. Okay, so I have no room, so maybe let me just add a new page real quick. Okay. So this becomes b1 hat times 0 minus 0, which is just 0, so we have 0 here, minus b2 hat times 0, which is just 0, plus b3 hat, which is 0 minus omega times x cosine theta minus L. So that means our cross product term becomes negative omega x cosine theta minus L b3 hat. So we can just put that back up here as negative omega x cosine theta minus L b3 hat. Okay, so I would also say that another trick to the cross product, if that was like kind of over your head, it's totally chill to just do this method. I'm pretty sure it's a lot faster, but it's just once you get to more complicated stuff, it just becomes very messy. So, yeah. But, I mean, in this case, you would know also that you would have a B3 term, because if you have B2 crossed with B1, that should give you the B3 term. It's like if you have B1 cross B3, you should get a B2 term. It's just a sign that is like sometimes tricky to figure out. And then also if you have a B2 cross a B2 or a B1 cross B1, B3 cross B3, that would always equal 0. So that's how another way you can verify that, you should end up with only a B3 term because you have a B2 cross with a B1 and then a B2 cross with a B2, which would give you 0. So the B2 cross B1 is going to give you the non-zero B3 term. Okay, if all else fails, try the determinant method because it's pretty straightforward once you learn determinants. Okay, great. So now we have this expression for V, B, and E. So that gives us x dot cosine theta B1 hat plus x dot sine theta B2 hat minus omega x cosine theta minus L B3 hat. Oh yeah, that's right. So that's our answer for the velocity. Oh gosh, so the velocity of B with respect to the E frame. So we can just box that as our answer for the first part. Okay, so I know we just found the velocity, but something that I think is important to reference is this problem statement where it says constant speed V. So the change in x, right? So x dot is going to be equal to, like some velocity, right? So in this case, because the ball is going down the hill, you'd expect x dot to be negative, right? But here, they also given this problem this constant speed v, and it's pointing downhill. So this can be a source of confusion, but the key thing to know is that speed is not a vector, so it's only a magnitude. So you won't have like a negative speed. So that's why v is going to be positive. And we know that x dot is equal to the velocity, right? So x dot is equal to v. But because x dot is decreasing, there's going to be a negative sign here because v is greater than 0, but x dot has to be less than 0, so that means that there needs to be a negative sign. So x dot in this case is going to be equal to negative v, so another way of writing this is negative v cosine theta b1 hat minus v sine theta b2 hat minus lambda, or not, I keep calling it every single thing except its actual name, omega times x cosine theta minus L b3 hat. That's another way of writing this, but I think for this problem, just stick with this form because it is defining the problem already, and this is going to be the most clear to understand, and it will also be the clearest for the next part of this problem. So just so I can explain this again because I'm not sure if it was super clear. Okay, so because we know that the ball is rolling down at a constant speed v, because of the speed, v is going to be positive. It's just a positive quantity for how fast the ball is going down this ramp. It's also constant. So that means that we can say that the change in the position, x dot, is just going to be equal to this constant speed v. However, x dot, the change in x dot, right, over time, x is getting smaller, right, because the ball is rolling down the ramp. So that means our x dot is less than 0, but we have a positive v. So that means that when we write x dot equals v, we need to add a negative to account for the fact that the position is decreasing. So this x is decreasing as the ball rolls down the ramp. So that's why we can have x dot equals negative v, and then we can plug that in here and then have this expression right here. But honestly, I don't really like that. So I think it's best to leave it in this form. And also, like, for this practice exam, the solutions also left it in this form, so maybe, I don't know, I feel like that's just the clearest way of explaining what's happening in the system. So I'm going to stick with the x dot version for the rest of this problem, just because it's easier to think about. But just a side note for that, because that's another way I think you could write the solution of this problem for the velocity. Okay, so now we can do the exact same thing again for acceleration. So let's remember how to do BKE. So the acceleration of the ball with respect to the E frame is a derivative with respect to time of the velocity of the ball in the E frame with respect to the E frame. How do we do BKE? First step, take the derivative of the vector. So in this case, this is the velocity vector. With respect to the frame, it is already written in. What is it already written in? It's written in the B frame. So that means we take it with respect to B. Okay, so first we took it with respect to the B frame, the derivative, and now we add the angular velocity of the frame it is written in, which is the B frame, right? So we take the angular velocity of the frame that this velocity vector is currently expressed in, which is the B frame, and we take that with respect to the E frame. So the angular velocity of the B frame, which is the E frame. Cross product with the original vector, which is velocity of B with respect to E. Okay. Oh, this is going to be fun. Okay, so we have x dot cosine. Okay, so I'm going to forego some of the writing here and just assume that you know that VB is going to be equal to this. So what is the derivative of that? So the derivative, we do product rule. X double dot cosine theta plus x dot sine theta negative sine theta times theta dot. And then that is all for the B1 hat term. Then we add x double dot, this is for the second term, the x dot sine theta B2 hat term. We take a derivative, we have, and also do product rule. So we have x double dot sine theta plus x dot cosine theta times theta dot B2 hat. Then we minus the omega times x dot. So basically we can do product rule again with this, except this is a kind of annoying product rule. So what to make this easier is we know that lambda is constant, L is constant, and theta dot is constant. So that just means we can simplify this into negative lambda. You can simplify this to lambda x dot cosine theta B3 hat. Because this term, they're all constants, so they're just constants. We treat them as constants. And so that is the third term. So then again, you can eliminate this because theta dot is 0. And we also know that x dot is equal to the velocity that it's going down at. But x double dot is just going to be 0 then because velocity is constant. So this v is constant. So that means that the x dot terms also go away. Okay, so now we have to add the cross product term. Let's not forget about that. So this term right here, so just all that stuff here. So we're gonna have same, what's the angular velocity of the B frame with the E frame? We already found that up here. Oh my gosh. Okay, so we found that up here, right? Again, you can try this again, curling your fingers in the direction of this rotating thing. And your thumb should be pointing in the B2 hat direction because it's rotating like into the page. So we had found that before to be omega B2 hat. Cross with your velocity vector. Your velocity vector is x dot cosine theta B1 hat plus x dot sine theta B2 hat minus omega x cosine theta minus L B3 hat. Cool. So, yeah. So we are left with omega x dot cosine theta B3 hat plus this ugly cross product. So, okay, so actually now that I think about it, it probably does save time to just like in this case, I just do the 1, 2, 3 like circle thing. But I'm just going to go through the determinant thing one more time, but a bit faster this time. So B1 hat, B2 hat, B3 hat. Put the first vector in, 0, omega, 0. Second vector in, x dot cosine theta, x dot sine theta. Ooh, I forgot a negative here. From up here. Okay, anyways. And then negative omega x cosine theta minus L. And then when we take this determinant, we have B1 hat equals omega times negative omega x cosine theta minus L minus 0. Right, we do this multiply minus this. Then same thing, but for the B2 hat, we have to put a negative sign in. So then now we do this and this. So we do 0 times negative lambda, or not lambda, omega cosine theta minus L minus 0 times x dot cosine theta, which is just 0, plus B3 hat. We would then take the determinant of these two. So this multiplied minus this multiplied. So 0 minus omega x dot cosine theta. Okay, so this ends up being negative omega squared x cosine theta minus L B1 hat minus 0 B2 hat, so we just ignore that, plus negative omega x dot cosine theta B3 hat. Okay, this is our cross product term, so we can put that up here. Minus lambda squared x cosine theta minus L B1 hat plus negative lambda x dot cosine theta B3 hat. Did I mess up something? Nope. Okay, so we're good. So now we can simplify this. So I can write this now as lambda squared L minus lambda squared cosine theta times x B1 hat minus 2 lambda, not lambda. I cannot figure out how to say omega. Okay, so that is our simplified result. So this, I think, let me check what it matches. Yep, so this matches with our solution. So we have the acceleration of B with respect to E is equal to this. Okay, so that's our answer to this problem. Just as a recap for the BKE steps. So the first thing you do in any kinds of problem like this is define a reference frame that is rotating with your system. So I think a good rule of thumb is to have one new frame for each rotation. So in this case, we only had one rotation, right? It was just the ramps, not the ramp, like that disc thing spinning around with the ramp on top. But that was the only angular rotation. So you had introduced one frame. So we introduced that at this, center of the disc. And we picked a point that is stationary in the frame that we want to find the velocity with respect to. So in this case, we wanted to find the velocity with respect to the E frame. The E frame is fixed in the ground, and so we need to find a point that is fixed in the ground, so fixed with respect to the E frame. We picked that point to be this point here because it is not moving. Obviously, it's just at the center of the disk, so it's not moving. And then we write first our position vector, which is going to be from O, our fixed point, to the point of interest, which is B. Then we write that out. We take the derivative of that to get velocity of the B with respect to the E frame. We apply the BKE here, simplify, get the result. And then to get the acceleration, we do the exact same thing to do BKE and simplify and end up with this. So, yeah. I'm not going to lie, these BKEs get more complicated when you move forward, so please learn them well at the beginning. So yeah, that's this practice exam. Hope it was helpful.